Hello, grade 12s. This is our first lesson for our new unit, chemical equilibrium. We're going to dive right into it. I'm just going to let you know that I'm going to divide this lesson into two parts. Our first part is going to look at the background concepts, and our second part is going to then look at some calculations that will conclude this lesson. So let's start. Okay, a good segue from how we ended our previous thermochemistry unit was looking at chemical kinetics. Now that will segue into today's topic, equilibrium, because we're going to look at forward and reverse rates of reaction as we begin to talk about and to define what equilibrium means. All right, so chemical equilibrium, when we're studying that concept, it's mostly referred to as a closed. Well, we have to use a closed system, not an open system usually. Although we will talk about how we can influence a chemical system. In that case, it would have to be open. We're mostly going to be looking at closed systems where matter can't escape or enter a chemical system. Energy, however, can be transferred. All right, let's move on. So when an important concept is one called a dynamic equilibrium. Now, that means that as a rate, right, back to chemical kinetics, as a rate of a reaction changes. What we're usually used to seeing since you started talking about chemistry, grade 8, grade 9, or even before, is you usually saw that a reaction proceeds in a forward direction from A reactant to B product. What we learned in our last unit was that this can happen at a certain rate, and it can be influenced by the concentration of our reactants. So the forward rate of reaction is what you've always usually seen. The chemical reactions you learn in grade 9 don't usually go backwards. But sorry, we're teaching you in steps. We're not necessarily lying to you, but this can also happen. Products can become reactants. Okay, so when a balance is reached between the forward and the reverse rates of reaction, that's called your equilibrium or your dynamic equilibrium. So the reaction has reached a state of equilibrium. And this happens when the rate of the forward reaction, right, is equal then. So rate forward, call that rate F, is equal to your rate in the reverse direction. When that becomes the same, we see a net zero change. Right? So the concentrations of both reactants and products, they will change all the way until that point where the rates forward are equal then to the rate reverse of the reaction. Okay, so that is a dynamic equilibrium. So this is just again showing that although you may look at a reaction or at a substance at equilibrium and not see that anything's changing, in reality there are reactants are becoming products and products are becoming reactants, and there is a movement back and forth in a way though that doesn't appear like anything is changing. There are a few kinds of equilibrium. We are going to talk about all of them and do examples, calculations as well, but we are going to focus mostly on one. So we'll talk about the first, solubility equilibrium. That's referring to when a solute and a solvent exist. So solute put into a solvent, and the rate of dissolution, or of, you can rephrase that, the rate of a solute dissolving into a solvent is then equal. So what you might see in a flask, probably a better drawn flask, but what you look at in a flask is you see a solution. Now this solution may look homogeneous, completely uniform, but what's actually happening here is solute is being crystallized, right? And it is also dissolving back into your solution. So it doesn't look like anything's changing, but in reality it is, just at a certain equilibrium. What if the solution is supersaturated and there are some crystals that already exist? Well, what's happening here in this case is you're getting perhaps more. It's moving around a bit. You're getting more crystallization than you are solubilized crystal. Okay. Now let's see. Okay, there, back to normal. All right, phase change or a phase equilibrium just means, well, here you have a flask of water. You may not see that anything's changing, but in reality, what we see is we see evaporation happening, and we also see condensation happening. And although nothing looks like it's changing, it actually is. All right, we'll look at examples near the end of the lesson when we talk about then how we did also in our last unit, ice converting to water or ice melting into water. There were some thermochemical aspects, concepts that we referred to in our last unit. Here, we're going to see that ice can turn into water, and now we're going to talk about this in a whole different way by looking at it through a different lens, an equilibrium lens instead. Okay, nothing too much going on here. I like pointing out a few things. What you've probably heard of course, heard of melting and freezing, vaporization, condensation. We just talked about sublimation, perhaps something that you haven't heard too much of. Deposition from a gas into a solid. So just different phase changes I thought would be interesting to share. All right, as you probably thought, this is what we're going to focus on the most, on chemical equilibrium. Right, and that is again when forward rates of reaction are equal then to the reverse rates. So forward means again moving from left to right, reactants to products, and reverse from right to left from products to reactants. Right, and when they occur at the same rate, there's really no change in the concentration. So it might not look like anything's happening, but in reality, there is movement. Okay. Now I like these sorts of graphs because it's shown you, well, this you've seen, you saw a few slides ago, but the forward rate of reaction for moments as the reaction's proceeding or moving forward, you see that the forward reaction has there's a higher rate of reaction when the reaction first starts, or higher rate in the forward direction compared to your reverse. Now, as time passes, your reverse rate of reaction increases until they both reach a state of dynamic equilibrium, which is approximately here, right? And although the rates are moving are equal, and we do see movement back and forth, your concentrations may not look like they're changing at all. Now, this is rate versus time. If we look at amount or concentration versus time, they don't have to be exactly equal. So another way to express this is we can have the amounts can be the same, although they're often not. They can be the same or very similar concentrations of, let's say, reactant A and product B. They're usually not. So at equilibrium, your concentrations of your reactants don't have to be the same as the concentration of your products. They just can't change once you've reached equilibrium. Okay, summarize that here again. So rates are the same. They're constant. Concentrations don't change once this dynamic state of equilibrium has been reached. Okay. Now a bit about what you've done in the past, and especially referring to grade 11. In grade 11 talked about limiting reagents. What you're actually going to see here is that a state of equilibrium can actually be reached before your limiting reagent has been completely consumed. Okay, that means then that maybe what you thought was occurring in grade 11 it wasn't the whole story, and sure enough it's not, right? There is more to stoichiometry than what you learned in grade 11. There will be some stoichiometry in this unit, just not currently, right? So stoichiometry makes an assumption that although it might be true in some cases, it has to be looked at now in a different way. So a stoichiometry question would assume that the forward rate of reaction is almost completely favored, so that A will completely become or almost completely become B, that nothing is going to go in the reverse direction, or very little or an insignificant amount will go in the reverse direction. Now this is the assumption made when we do stoichiometry problems, okay, as you saw in grade 11, right? So again, not lying to you, just teaching you in steps. Okay. Another example, again, how concentrations just have to, at a point of equilibrium, stay constant. Not the same, but constant. Okay, so once equilibrium has been reached, a percent yield, similar to what you did in grade 11, can be determined. And that is the actual product or the actual concentration of your products at equilibrium, that is the real measure of what your percent yield is. Now, these concentrations can be divided by the theoretical yield of the concentration of your products, and that would give you your percent yield. Okay, and we'll continue then with these examples. Okay, so that's just part one. We have a few examples to go over, and I'll explain why I have these pictures here, and hopefully it'll help you remember how to solve the problems that are going to come up.